Last time, we gave a technical-looking condition for when a function defined on the dyadic rationals is actually Hölder continuous of some parameter alpha. As a reminder, here's that condition now. A function omega on the dyadic rationals in the unit interval, taking values in some complete metric space S, is alpha Hölder continuous if this constant is finite. And here, these delta n's are the maximum mesh of the function omega on the dyadic rational partition of width 1 over 2 to the n. That is to say, delta n of omega is the maximum distance between omega of s and omega of t for all s and t that are no more than 1 over 2 to the n apart, where s and t are in dn intersect the interval from 0 up to 1. And this is the finite set of dyadic rational numbers whose denominator is no bigger than 2 to the n. In particular, we showed that if that constant is finite, then the function omega is C alpha on the dyadic rationals, and in fact has this as at least an upper bound for its alpha Hölder modulus of continuity. Now we also saw that owing to the completeness of the metric space S, if we have an alpha Hölder continuous path omega defined on this countable dense subset, then it will have a unique alpha Hölder continuous extension to the whole unit interval, indeed with the same modulus of continuity. This gives us our path forward to guaranteeing the existence of Hölder continuous versions of stochastic processes under appropriate assumptions. And those assumptions will actually only depend on the two-dimensional distributions of our process. That is, the distribution of the random vector xt, xs for any pair s and t in the unit interval. Here is the theorem that will make that work. Suppose we have a stochastic process, which for now we'll assume is only defined on the dyadic rationals in the unit interval, taking values in some complete metric space. If there are positive constants epsilon and c, and a p greater than 1 plus epsilon, with the following inequality holding true, that the LP norm to the pth power of this random variable here, the distance between xs and xt, is bounded by that uniform constant times s minus t to the 1 plus epsilon, again for all s and t in the dyadic rationals. Then, for all appropriate alpha, we will find that the path t mapping to xt is alpha Hölder continuous. And those appropriate alphas are exactly the ones that are less than epsilon over that p. We can more precisely state this as saying that for any alpha in that interval, the actual random distance between xs and xt is bounded above by a certain constant here, which is not constant, it's a random variable as well, times the alphath power of s minus t, where that random variable, k alpha of x, is actually in LP. The upshot there is, since it's in LP, that means that it is almost surely finite. And so we get, on a set of outcomes of probability 1, that the path xt as a function of t is alpha Hölder continuous for t in the dyadic rationals. Now, as you can imagine, that k alpha there is going to be the k alpha that appeared in that technical proof in the previous lemma. So let's explore how that works. Here's a restatement of the theorem, and I've actually been more generous here and only insisted that p be greater than or equal to 1, but we may as well assume that it's greater than 1 plus epsilon. The reason is, as you will show on your homework, that if p is less than 1 plus epsilon, and this inequality here holds true, then in fact xt is better than alpha Hölder continuous, xt is constant, almost surely. So that's kind of the boring case. Therefore, we may as well assume that the p that we'll choose should be bigger than or equal to 1 plus epsilon. So, as I said, we're going to define this k alpha of x to be that k alpha that we computed in the previous lemma. That is to say, for each omega, we can now think of the stochastic process xt in the outcome omega as a path. It's the function t maps to xt of omega, the coordinate process. And so that path has a maximum mesh on each dyadic interval of width 2 to the n, and therefore we can compute this k alpha function, which I'll write explicitly again. That's 2 to the 1 plus alpha, the sum n going from 0 up to infinity, 2 to the n alpha delta n of the path xt of omega, which, to be clear, is a random variable. It depends on the particular omega chosen there. So we're going to, for the sake of brevity, write this as delta n of x as a random variable of the outcome omega. And now we're just going to compute and estimate its LP norm. If I take the pth power of the maximum mesh delta n of x, well, again, that's just taking the maximum over integers between 1 and 2 to the n of the distance between I over 2 to the n and I minus 1 over 2 to the n image under the path x, of course, to the pth power here. And now we'll make the following extremely blunt estimate that the maximum is less than or equal to the sum of these positive terms. And therefore, we'll take expectations of both sides of that inequality. Now, by the assumption of the theorem, the expected value here is less than or equal to c times this minus this to the power 1 plus epsilon. But that minus that in absolute value is always equal to 1 over 2 to the n. And so we get that this is less than or equal to the sum I going from 1 up to 2 to the n, c times 1 over 2 to the n to the power 1 plus epsilon. And here's the deal. This is a sum of 2 to the n constant terms. They're equal to 1 over 2 to the n times 1 over 2 to the n to the epsilon. So that's equal to c times 2 to the minus n epsilon. And therefore the LP norm, which is just the pth root of that expectation, I get that that's bounded by the pth root of this, which is this quantity right here. So therefore, this random variable here, k alpha of x, its LP norm, using the fact that the LP norm is a norm, is less than or equal to, well, I can take this constant out front and push the norm through the sum and put that constant there, and I just have to measure the LP norms of these guys, which I've got right there. So that works out to be less than or equal to And now, fortunately, our assumption in the theorem was that alpha is less than epsilon over p, which means that I have an overall negative exponent of 2 to the n there, and so that sum will be finite. In fact, we can calculate the bound explicitly here. It's going to be c to the 1 over p times 2 to the 1 plus alpha over 1 minus 2 to the alpha minus epsilon over p. And whatever that is a finite number. So we've shown that k alpha is an LP random variable. LP random variables are almost surely finite, and so this is almost surely finite. Now, we proved in the last lecture that we do get this inequality holding for that k alpha. And so on the probability 1 event that this is a finite random variable, that shows that the path t maps to xt is indeed Hölder continuous of parameter alpha on the entire dyadic rational set in the unit interval, and that this random variable is at least an upper bound for its Hölder modulus of continuity. That concludes the proof of this theorem. But what is that really good for? Well, what we'd really like to do is start with a stochastic process, xt, not just defined on dyadic rational t, but defined everywhere, and show that that process has a continuous version. Well, how we're going to do that is take that process, restrict it to the dyadic rationals. If we have this condition holding, as we just saw, that shows that on the dyadic rationals, that process is Hölder continuous. Well, that means by what we proved in the last lecture, that it will have a unique extension to a Holder continuous function on the whole unit interval. And that extension of the restriction of x is going to be the version that we seek. But we have to do one further extension because we're interested in this not just on the unit interval, but on the whole positive real line. We're going to do that extension in 2 steps. First, we're going to extend it from the unit interval to the interval from 0 up to t for any natural number t. And once you can do that, you can then let t go off to infinity and go to the whole non-negative real line. And that extension there is going to be on your homework. So putting things together, here is the main result that we've been aiming for, which goes under the name Kolmogorov's continuity criteria. For any large integer end time t, if we have a stochastic process on the interval from 0 up to t, taking values in a complete metric space that satisfies the following estimate. There are some constants, epsilon and c positive, and some p greater than or equal to 1, but again, we may as well assume that it's greater than or equal to 1 plus epsilon, otherwise we get the even stronger condition that the process is actually constant, such that the LP norm to the pth power of the random variable, which is the distance between the process at any 2 times, is bounded by s minus t to the 1 plus epsilon times the constant c. Under those circumstances, for every parameter alpha between 0 and epsilon over p, there is a random variable, k alpha of x in LP, and a version of the stochastic process xt, defined on the whole interval from 0 up to t, that is alpha Holder continuous with k alpha as its modulus of continuity. This is going to be our main workhorse for constructing continuous processes. The beauty here is that in order to guarantee that a certain process has a continuous version, we just need to check this metric condition that only involves understanding basic properties of the 2-dimensional distributions of our process. Now, we proved the result that we're going to use here about k alpha being an LP random variable in the context of the dyadic rational interval up to time 1, but that's going to suffice to prove the extension to this larger interval because we can just do that estimate separately on intervals of length 1. But we've got to be careful at endpoints. We could have 2 intervals where our map is Holder continuous, but is very badly behaved at the boundary. Even if it's continuous there, it might not be Holder continuous. But what we can do is instead use overlapping intervals. So we have an interval of length 1, and then another interval of length 1, and then another interval of length 1, so that every point where we do this is in the interior of one of those intervals, and then we'll be able to piece these arguments together. What's more, all the inequalities we're interested in are manifestly translation invariant. If I shift s and t both by some parameter, then the inequality remains unchanged. And so putting those things together, if we can prove this result holds on the interval from 0 up to 1, we'll be able to extend it to the interval from 0 up to t for any integer t. So now let's focus on proving this on the unit interval. Well, we basically did that already in the dyadic rationals. We showed that there is an LP random variable, k alpha of x, with the property that this Holder alpha continuity inequality holds for all s and t in the dyadic rationals. And so on the probability 1 event that this LP random variable is finite valued, that means that this path, t maps to xt, is alpha Holder continuous on the dyadic rationals. But because this path is taking values in a complete metric space, there therefore exists a unique C alpha extension to the full unit interval, as we proved in the last lecture. We will call that extension of the restriction of this path back to the unit interval x twiddle. And by what we proved in the last lecture, it satisfies the same Holder continuity estimate with this modulus of continuity on the whole unit interval. So to conclude our proof here, it just suffices to show that this extension of the restriction, x tilde, is actually a version of the original process x. That is to say, we just need to show that the probability that xt is not equal to xt tilde is 0 for each fixed t. Well, we'll do that metrically. Let's look at the distance between these two and in fact take its pth power. That's going to be good enough to check whether or not this is 0. And we'll notice that inside here, we can use the triangle inequality and compare that to x at any other time s. That is to say, that's going to be less than or equal to the distance from xt to xs plus the distance from xs to xt tilde, all to the power of p on the outside. So that's true for any s that we'd like to choose. And therefore, if we take any sequence of s's that are dyadic rationals and that are converging to t, we'll get this inequality holding for those, which means that this will be less than or equal to the lim inf over such s's tending to t. Well, if s tends to t, since x tilde is defined to be a continuous extension of x on dyadic rationals like s, continuity of the metric d tells me that this term is going to go to 0 in that limit. And so this will be less than or equal to the lim inf of just this to the pth power. Now that's a pointwise estimate we've just made. We're going to now take expected values. And this is a lim inf, which means that we can use Fatou's lemma to put that lim inf outside the expected value. Now we use the Komogorov criteria, which tell us that this expected value is bounded by a constant times s minus t to the 1 plus epsilon. But as s tends to t, this, of course, goes to 0. So what we have is that the expected value of this non-negative random variable is 0, which tells us that it is almost surely equal to 0. That is to say, the probability that xt is not equal to xt tilde for this particular value of t is the same as the probability that the distance between those two is strictly positive, whether you take a pth power or not, and that is just 0, which shows that x tilde is a version of x, concluding our proof. And what that means, ladies and gentlemen, is that we have finally constructed real Brownian motion. Remember, pre-Brownian motion is a process we constructed, BT, a stochastic process indexed by positive time, taking values in RD. We constructed it as a Markov process, but it's just an independent increment process. The increments are normally distributed with variance t minus s when t is greater than s. And actually, regardless of whether the increments are independent or not, this is already enough information in order to calculate what we need to check Kolmogorov's criterion. As we know, we can construct a normal random variable with variance scaled by any positive number there just by taking the square root of that number times a standard normal. And therefore, we can just compute here for any positive number p, the expected value of the Euclidean distance between bt and bs to the pth power is going to be t minus s to the p over 2 times the expected value of the Euclidean length of z to the p. Now, this is some Gaussian integral that probably is hard to compute exactly for non-integer values of p, but that doesn't bother us at all because this is just some constant with respect to the underlying process, bt. And therefore, if I take any p greater than 2, we note that p over 2 is 1 plus p over 2 minus 1, and that's positive. That's going to be our epsilon. And this is exactly Kolmogorov's criteria. The expected pth power of the distance from bt to bs is less than or equal to a constant times t minus s to the 1 plus epsilon for some positive epsilon. That tells us that there exists a continuous C alpha version bt tilde of the Brownian motion for any alpha less than epsilon over p. Epsilon is p over 2 minus 1, so this is 1/2 minus 1 over p. Well, p was actually arbitrary here. We could take p as large as we like and still find some constant depending on p for which this holds. And so since we can make p as large as we like, we can therefore take alpha as close to 1/2 as we want. And so we have proved this landmark result that there is a version of Brownian motion that is Hölder continuous with any parameter strictly less than 1/2. We will soon see that we can't make it Hölder 1/2 continuous. So this is a sharp result. Now, before we sign off on this, let's, as a sanity check, see what happens if we try to apply Kolmogorov's continuity criteria to a process we know can't be continuous, the Poisson process, nt of intensity lambda. Remember, that is a process that has independent increments as well. If s is less than t, then the increment nt minus ns is Poisson distributed with rate lambda times t minus s. Well, that means that we can exactly calculate, if we work hard enough, the expected pth power of the distance between nt and ns. It's just going to be the pth moment of the Poisson distribution right there. And we can approach this in any number of ways, but using, for example, the moment generating function or the characteristic function that we have computed in the past and doing a little bit of calculus, we can check that for any integer p, this sum here is bounded above and below by constants times lambda times t minus s for small t minus s. In particular, we can simply never make this less than or equal to a constant times t minus s to the 1 plus epsilon for any strictly positive epsilon. This is always of order t minus s to the 1. And we need to have a strictly positive epsilon for Kolmogorov to work. So the Kolmogorov continuity criteria does not apply to the Poisson process, which is good because, as we expect, it simply does not have a continuous version. Before we move forward with this now fully constructed continuous Brownian motion and study its properties, we're going to stay in the realm of Kolmogorov's criteria a little longer and develop some related tools for studying the convergence of sequences of continuous stochastic processes.